Hello, in this video I'd like to talk about various perspectives on non-deterministic tree automata. In the previous video we saw that non-deterministic root-to-leaf tree automata and non-deterministic leaf-to-root tree automata were not only equivalent to each other, but they were essentially expressing the same thing, and we can unify those definitions as follows. So again, we're going to define these things as tuples. We're going to have some finite alphabet, some finite set of states, some transition relation, and a set of root states. And we're going to accept a tree word if there's an association of states in our set of states to each of the nodes of the tree. That is, there's some sort of run of the automaton such that the root gets a state in our set of root states. And for every node, if we look at that node and its children, the symbol at that node, the state at that node, and the states at the children satisfy the transition relation. And of course, if there isn't a left child or there isn't a right child, we can indicate that with octothorpes, and the transition relation has to accept not only states in these positions, but also octothorpes. It's worth noting that we don't need a special character like an octothorpe as an end-of-branch character that we can feed into our transition relation to indicate that there isn't a left or isn't a right child. We could instead have a distinguished state within Q that gets assigned this particular role. Kind of like a starting state, I'll call it an end-of-branch state. In my series on word automata, I described something called a triangular constraint system, and this is essentially that. A triangular constraint system was a way of assigning states halfway in between the characters of a word, such that if we look at a state, and then the character after that, and then the state after that, that always fell within a particular collection of allowable triangles. And we're essentially doing the same thing here, except there's two differences. First of all, I've shifted the character half a step over so that it's at the same position as our state. And that's important. While it does make sense when talking about tree automata to have states on the edges of the tree, that's kind of where they want to be. When we do the translation to monadic second order logic, we're going to have to shift everything half a step over. If you remember in my original video series, the time that we had to shift everything half a step over was when we started talking about the equivalent first and second order logics. So it's going to make that step of the translation much easier if we just move everything half a step over initially, so that our symbols and states are located in the same location. And then of course the next difference between this and a triangular constraint system on words, well, a triangular constraint system on words constrained between the state at one position and then the symbol halfway on to the next state, and then the state at the next position. We had these sorts of constraints. But for a tree, the states at the next position, well, there could be two of them if there's two children. But this definition here is a little bit asymmetric, and that's fine. When we're talking about our particular trees, they have a directionality to them, right? They have a notion of root word and a notion of leaf word. They have a notion of up and a notion of down, and those are distinguished from each other. But it kind of makes sense in preparation for maybe we want to generalize our definitions here, our concepts of constraint systems, to situations where we don't have a distinguished notion of up and down, and so we shouldn't really be distinguishing between the parent node and its children nodes in our definition. And so instead, maybe it makes sense to think about something I like to call a local constraint system. I'll define these more formally in a much further video, but for now I want to say that a local constraint system, we're constraining whenever we have some sort of local region of our structure, in this case a parent node and its two children nodes, or maybe lack of children nodes, or maybe even lack of parent nodes. If we have a node that doesn't have a parent, then that node has to be the root, and so we want to constrain what sorts of states the root gets. Anytime we have a local configuration like that, if we look at the characters that came associated to each of those nodes and the states that we're associating to each of the nodes, then together all of that information is accepted by our transition relation. There's some finite number of configurations like this, and again, modified versions that are missing a left child or missing a right child or just missing a parent. And we want to label states onto our tree such that every local configuration falls into this finite set of allowable configurations. We can similarly make sense of this definition on words. Imagine we have some sort of word, then we're trying to associate states to all of the positions in that word. Again, you can think of this as a line graph where we've associated a character to each of the nodes, and we're now going to associate a state to each of those nodes as well. Such that when we look at every local region, that is a node and its neighbor, the characters and states at those nodes fall into some finite collection of allowable configurations. And of course, if a character doesn't have a neighbor to the left, then there's a separate set of allowable configurations there, and if a node doesn't have a neighbor to the right, then there's a separate set of allowable configurations there. And so we say that a local constraint system accepts a word if there's some association of states. Again, this is like a non-deterministic thing, so you have to try all possible sequences of states. If there's some association of states to all of the positions such that every local region falls within some allowable collection, or equivalently satisfies a transition relation. And there's some sort of relationship between the underlying monadic second-order logics and what constitutes a local region for the purposes of local constraint systems, but I'll talk about that in a future video. Another perspective that was incredibly helpful when we were thinking about finite word automata, but hasn't really shown up when I've been talking about finite tree automata, is the transition diagram. Transition diagrams allow us to make a connection between automata and graph theory. If we have some sort of graph with a bunch of directed labeled edges, labeled with characters from some finite alphabet, and we designate some of the nodes in the graph as start nodes and some of the nodes in the graph as end nodes, and we look at the set of all paths from a start node to an end node, those are going to have labeled edges, and so the labels of those edges are going to form words because it's an ordered path, and then we take all of those words, and that's a regular language. And it's not just any language. We can interpret our graph as a transition diagram for a non-deterministic finite state automaton, and it's the language accepted by that particular automaton. So transition diagrams allow us to make a connection between regular languages and paths through labeled graphs. But can we make sense of this information for tree automata? The answer is yes, but it's a bit gross. Let's say that we wanted to make sense of a transition diagram for the really simple automaton we had a few videos back that tells us if a tree word has an odd number of A's in it or not. This automaton is incredibly small. It has only 2 states and it only has 2 characters in its alphabet. And yet, when we try to make its transition diagram, it's going to get quite complicated. Instead of drawing labeled arrows between states, we need to draw labeled kind of merging arrows between states. So for instance, if we wanted to indicate that when the left child is labeled 0 and the right child is labeled 1 and a node is labeled A, then we want to go into state 0. And we'll do that using this sort of an edge here. Now, very conveniently for us, for this automaton, if the right child is labeled 0 and the left child is labeled 1, and we read an A, we also go into state 0. The order of the children does not matter. And so that's going to save us from having to draw a whole bunch of arrows that we normally would have to draw, making our diagram even more complicated. If we have two child nodes in state 0 and state 1, and we read a B, we're going to want to go into state 1, so we indicate it like this. If we have two child nodes in state 1 and we read a B, we're going to want to go into state 0. If we have two child nodes in state 1 and we read an A, we're going to want to stay in state 1. If we have two child nodes in state 0 and we read an A, we're going to want to go into state 1. And if we have two child nodes in state 0 and we read a B, we're going to want to stay in state 0. So this is the absolute minimum the diagram could be. We have a choice here. We also need to indicate all of the entries of the transition table that involve octothorpes in them. And we could add a whole bunch of edges that have octothorpes on them, or we could designate 0 as a distinguished start state. So whenever we would enter an octothorpe into the transition function or transition relation, we would enter a 0 instead. And then we can get away with this nice simple diagram, making all of these concessions and using this really simple example. We get this really gross, kind of hard to read diagram for our automaton. On the other hand, if we want to add in the octothorpes, it winds up looking like this, or if we want to unmerge the octothorpes, it's a little bit nicer, it looks like this. And of course, we haven't even gotten into the case where our automaton is non-deterministic, but you could certainly indicate that on a diagram. You just have maybe multiple arrows either coming out or multiple branching arrows connecting two states. If you wanted to indicate that if we have children in states 0 and 1 and we read a B, we could also wind up in state 0, you could indicate an edge like that or just draw another one of these things. But thank goodness that's not what we have here. And just like how with ordinary non-deterministic word automata, we could make sense of paths through graphs from start states to end states, we can also make sense of embedding a tree word into one of these transition diagrams. Just to make things work out nicely, I'm going to wind up adding special end of branch characters onto the end of every branch and a special root character onto the root, just so that we can keep track of where these ends are. Again, when we're talking about ordinary paths through graphs, ordinary non-deterministic word automata, we're very specific about where our paths can start and where our paths can end. Well, we need to be specific about that information in the tree transition diagram case as well. And so I'm going to add these bits of information onto our tree just to make them easier to keep track of. And as we can see, we can fold a tree up into this diagram if and only if it's accepted by our automaton. I'll link below to an interactive where you can see a bunch of trees folding up into this particular transition diagram. I'll also link below to an interactive where you can play around with local constraint systems and triangular constraint systems on trees. So hopefully you can get a better sense of how they work, and they form kind of interesting puzzles. So thanks for watching. Be sure to leave any questions or comments you might have down below, and be kind to each other.